This is Robert Sapolsky, and you're listening to Father-Offspring Interviews.
Hello, folks. Welcome back to Father-Offspring Interviews, episode 64. To get started, we have questions from Richard from the UK/Brazil and Mustafa from Germany about chemo brain fog, the cognitive problems in cancer patients undergoing chemotherapy. So, why does it happen, and are there treatments for it?
Well, chemo brain, more formally, cancer-related cognitive impairments, chemotherapy-related cognitive impairments is a very typical feature of people undergoing chemotherapy. Cognitive problems. Okay, so review. What is cancer? Because this winds up being informative as to what the chemotherapy is doing. So you're a young organism, you got all sorts of genes that are involved in growth, making you grow, your body grow, making your cells divide and make new cells. All of that's going on as a normal part of growth, maturation. And then at some point, you turn into something more mature than that. And all these growth related genes are silenced forever after, ideally. And what cancer is about is when something accidentally reactivates these growth related genes that have been quiescent since you were a youngin'. Something reactivates them, an environmental toxin, radiation, a gene that's already prone towards doing that because of mutation. This broad family called oncogenes. These are genes that should have been silenced forever when you were done maturing, and something triggers them into activating again. And suddenly you have cells dividing and growing like you're a brand new babe out in the world there, except you were many decades old, uncontrolled growth. And cancer is cells growing out of control in a way where fragments of this growing cluster of cells, tumors, can come loose, carried to someplace else, metastasize, start the same process there. Okay, so this is a general picture of what's happening with cancer. So the strategy with chemotherapy is a remarkably crude one, which is to throw a poison into you. The idea is it's a poison that is very good at killing cells that are dividing and growing fast, just like your tumor. So the strategy is to throw in enough of this poisonous stuff to kill the tumor, but not so much of the poisonous stuff that it kills you, and to kill the tumor before it kills you. So this is the still remarkably crude way that people go about doing chemotherapy. So all sorts of chemotherapeutic agents, and what they tend to do is they target cells that are undergoing cell division, ninth grade biology, mitosis. Cancer cells are undergoing mitosis like crazy because you've had this early growth profile of gene expression accidentally triggered now decades later. So, what these chemotherapeutic drugs do, these cytotoxins, is they do stuff like they take advantage of right when the cell is making copies of its DNA to divide into two, these drugs slip in and they sort of link the two halves of the DNA sort of helices that are being pulled apart so they can't do it, or they get in between and they disrupt the enzymes that are working to replicate your DNA. They just mess up the whole machinery of it. And there's all sorts of surveillance signals going on in the cell that says, whoa, we were happily starting mitosis. We were happily starting mitosis because we're a cancer cell now. And some drug just screwed up everything. It's all off the rails here. So let us activate some programmed death genes, and the cell kills itself. The cell is killed by the chemotherapeutic agent. And ideally, that's what you're now doing to all the cancer cells. Two ways you get into trouble at this point. First off, you're killing the tumor cells. These cells are bursting open and spilling their inflammatory guts out all over the neighborhood. And that's causing all sorts of inflammation related to trying to kill the tumor. But the other problem is that this is a drug that is simply good at fast dividing cells getting in and killing them. And even though the tumor cell is growing like crazy, there's still parts of your body that grows with some regularity, like your hair follicles, and a characteristic of chemotherapy. The drug attacks these fast dividing cells, fast growing cells there also, and your hair comes out. Okay, so we've got this general issue here of you are targeting really fast growing cells, the cancer, with a drug that is toxic to cells that are undergoing mitosis, that are dividing, that are replicating, and as collateral damage, also getting cells in your body that are normally undergoing rapid cell division rates, just as part of normal functioning. Okay, so that's great. Now we've got the problem coming in as to these drugs messing up cognition in the brain. Mind you, this is with chemotherapy, drugs like this. This is with radiation therapy. It is not with surgery that goes in to remove a tumor. It is not with what is termed immunotherapy, where there's now very specific antibodies against only the tumor itself. This is a general downside of this nutty, barbaric approach of let's throw in something that's going to poison the tumor before it poisons you and before the tumor kills you. You're in this race. So out of that comes all these cognitive problems that you get with chemo brain. And the question immediately becomes, how are some of these chemotherapeutic agents, some of the ones that are studied most often, doxorubicin, cisplatin, immediately there's two surprises in this literature. The first one is dogma used to be that most of these chemotherapeutic drugs don't get into the brain. They don't get past what's termed the blood-brain barrier. So if they're managing to mess up function within the brain, they're doing it by way of peripherally causing the inflammation mentioned before. They're causing tumor cells to be dying. This is very pro-inflammatory, and that gets into the brain, the inflammatory signals where they shouldn't be, but it gets in there and that causes problems. One bit of revisionism is when you read those early papers saying, well, the drugs don't normally get past the blood-brain barrier. Of course, unless there's something screwy with the blood-brain barrier. And it turns out what these drugs do is often cause something screwy to happen with the blood-brain barrier. So they're getting into the brain far more readily than people used to think. The second surprise is one that runs counter to this whole story. Okay, so you got neurons in your brain, and you've got all these support cells in there called glia. And as was even mentioned last week, neurons are post-mitotic. They don't divide anymore. There's a little cluster of stem cells in one part of your brain that makes new neurons, but your existing neurons do not undergo cell division. These glial cells do. So that generated this immediate obvious prediction that these cytotoxic chemotherapeutic drugs, either indirectly or managing to get into the brain, are going to be damaging glial cells, because glial cells are the ones that are dividing. And indeed, what you see is there's damage to some of the glial cells that form the white matter, the myelin sheath on axons throughout the brain. So you see loss of myelin, which makes for sort of disordered signaling, discoordinated signaling. You see these chemotherapeutic drugs are attacking the stem cells in your brain that would occasionally be dividing to make new neurons. So you're damaging the glial cells, you're blocking the genesis of new neurons. But what has surprised people is they appear to get into neurons as well. And even though the neurons are not undergoing cell division, which is what these chemicals are designed to wreak havoc with, they still wreak havoc. They get into the DNA and intercalate is the term. They get jammed in there between the two helices. They get in there and they screw up enzymes that are normally doing gene transcription rather than gene duplication. And the same thing happens. Alarms go off saying this is not right. Signals get to mitochondria, which get hysterical and release tons of oxygen radicals that wreak havoc with the neuron. And the end result is you get neurons that don't function very well amid the supporting glial cells being damaged and amid an inability to generate new neurons as a replacement. And you wind up getting the cognitive profiles of chemo brain, which is a whole variety of types of cognitive impairments, problems with concentration, problems with executive function, problems in all sorts of domains, because not only are your glial cells, but your neurons as well are being hammered by this toxin. So, what can be done about it? And the reality is at this point, not a whole lot. When you look at the recommended treatments, there's one easy domain, which is make sure some of the side effects of chemotherapy, for example, anemia, are not getting so severe that they are messing up cognitive function. Or people with cancer and undergoing chemotherapy, they get something called cachectic, which is basically they're losing weight faster than could be explained by their food intake. And they're not intaking much food either because they're feeling lousy. And this state of cachexia could mess up aspects of brain. Okay, so make sure the anemia is under control, the cachexia, that's sorted out. Good. The side effects that could be potentially affecting the brain. Next, you look and what's the advice, the therapeutic advice, all the usual things you would suspect that make you roll your eyes, which nonetheless collectively probably are kind of helpful and the best you can do. Make sure you're eating regularly, even though you have no appetite. Make sure you're getting enough sleep, even though you feel sick as hell and that's problematic. Go meditate, go clear your head, go get social support, the whole list of those things. I particularly liked one website, I think it was Mayo Clinic, that said make sure you prepare for success. That was an exact quote. But don't do something cognitively demanding at a time of day where you know by now you tend to be at your worst. Don't do something cognitively demanding. If you got lousy sleep last night, don't set yourself up for this being a self-fulfilling prophecy of your cognition even more impaired. A little bit of drug treatments that people are trying, none of which are approved, but they're all sort of in off-label usage at this point. One approach is some people find it helpful to be put on some of the drugs given to people with ADHD, like Ritalin. Something about speeding up cognition winds up being a little protective. There's a family of drugs which, when somebody comes down with Alzheimer's disease, they prescribe a drug called Aricept or a drug called Tacrin or a second generation called Memantine. Okay, so is there any good news in here? Yes, there is amid the bad news. The bad news is this is very, very common. I think most individuals undergoing chemotherapy have some cognitive impairments. And the bad news is it can persist for months or years. And the good news is we know that it could persist for months or years because part of this is sort of therapeutics for cancer is getting good enough that a whole lot more people are living long enough to get past this period and recover from the cognitive changes there. So that's the state of it. As you can see, that's a pretty dismal list of things to like do other than like don't get stressed and exercise your brain and your body and whistle a happy tune. um, Nonetheless, it seems to be transient, and the good news is that with many of these cancers people live long enough now that they can see that indeed it was transient.
All right, so now Bibiana from Spain asks, what happens neurologically and emotionally to people who use Botox on their faces when it comes to feeling emotions and being empathetic towards others? Do they have any alterations in brain areas, not in short term, but in long term?
Well, we've just looked at the incongruity of taking a powerful poison that's meant to kill a tumor before the tumor kills you. Here we have the incongruity of some people voluntarily having botulinus toxin injected into their faces, Botox, to paralyze their smooth out wrinkles. You look young and immortal, and Botox. And Botox has been the subject of a lot of studies now having to do with emotions. Okay, we start off with seemingly like a self evident question or something. How do we know what emotion we are feeling? And we know what different emotions feel like. But way back when, and way back how many episodes we've talked about this, William James teamed up with an otherwise obscure collaborator named Lang and came up with the James Lang theory of emotion, which is you have a certain state in your head of arousal, and it causes a change in your body's functioning. For example, your heart beats faster. And then how do you realize you're excited about something? Your brain realizes your heart is racing. Oh, if my heart is racing, I must be feeling excited. You decide what emotions you're feeling based on the information you are getting from your body. Term now used, interoceptive information. And that turned out not to be right. And it's sort of Jamesian extreme form that this is how you decide what emotion you're feeling. Because what people have been able to show is the speed at which, for example, your heart begins to beat faster in response to some circumstance is way slower than we where we are feeling excited. The time course doesn't work. But what people since then have realized is interoceptive information coming back to your brain about your bodily states doesn't tell you what emotion you're feeling, but it can tell you the intensity with which you're feeling it. And a classic example is people given adrenaline or a drug somewhat like adrenaline without knowing it so that their heart is racing. They pick up whatever emotional atmosphere is in the social setting they're in, but they feel it more intensely when they are having their hearts beating faster. So part of what is happening is indeed this James Lang theorem. So this now takes us even further back to Darwin. Darwin and then James came up with what is called the facial feedback hypothesis, which is part of how you're telling what your emotions are, part of how intensely you are feeling your emotions is what your face is doing, what facial expressions you are coming up with, which is again one step away. The original Jamesian formulation was, ooh, how do I know what I'm feeling? If I'm smiling, I must be happy. No, this is instead saying if I am smiling, it will make the intensity with which I feel pleasure or happiness get expanded. If I'm frowning, the negative feeling I am having will be enhanced, it will be augmented. And it turns out something like that is going on. For example, when you were having some feeling, some negative feeling, you were disgruntled about something, people typically do furrow their eyebrows. When people are pleased with something, they smile. When you are observing somebody else with a certain emotional state, you tend to have some of the same. You will frown if someone's frowning at you. Smiling evokes smiling, that business with mirror neurons that are probably responsible for this. So, what's the evidence that what your face is doing? Part of what your brain is being fed by is information about your facial expressions that are upping the intensity of the emotion that you're feeling. First sort of finding is when you look at people who have a facial paralysis so that they cannot smile, they have higher rates of depression than people who have facial paralyses anywhere else on their face. It's selective to paralysis in the smile there. Okay, so that's interesting. Then it gave rise to this study, a guy named Fritz Stack, a German psychologist, who came up with this very clever thing. He got people to do one of two things with a pencil. Either force them to do something resembling a smile. Here, hold this pencil between your teeth like this, and now you are generating something that looks like a smile, or hold this pencil between your lips, which pulls your mouth forward. So artificial. How did he get people to do this? He came up with this complete fakakta notion that we're doing a study about people who have lost control over their hands and thus how they could manipulate pencils in their mouths. They got people to do this, either putting a pencil in their teeth or in their lips. And then they showed them some cartoon, some humorous cartoon thing. And what they showed was if you had been forced into your face taking on a smile like expression there, you found the cartoons to be funnier than if you were holding the pencil with your lips in this pulled together gesture there. Okay, so that was pretty amazing. This was followed up by a study showing if you make people make different vowel sounds, ooh, ooh, is a very frowning sort of thing. People who were looking at humorous film clips while saying or ooh, the ones that pull your mouth away from a smile, people would find these to be less funny. Something about your brain is saying, how funny is this? Well, if my mouth muscles are doing this, this must be very pleasing. Okay, so this opened the way for people beginning to try to do some clever therapeutic things. And there's a small literature where you take people who are moderately depressed, and if you force them to smile, forced smiling over and over, it makes them feel a little bit better. Sufficiently so that there's like some school of this is a therapeutic approach. It's a very small effect, but this is part of it. So all of this was setting people up for finally the Botox experiments. So you've gotten Botox injected into a place in your face, which is then very stiff, very paralyzed. The sort of expressivity that you would be generating using these muscles doesn't work as well anymore. And where all of the research has been is what are termed the globular muscles, which are the frown muscles, a whole complex of muscles there, and which you pull them together when you frown. And I guess if you do that too much over the decades, you develop frown lines, and now you want Botox to get rid of your frown lines. So people would be injected with Botox in this muscle cluster there, and they don't frown anymore. And what the first sort of phase of the literature showed was you immobilize these muscles and people wouldn't perceive other people as being as disgruntled, as being as negative, because you can't mimic their frowning. Next, people would read some segment of something with some distressing news that you would normally frown over, and people would report afterward ratings of how intensely did that make you feel discomforted or whatever, and not as much happy, smiling, all of that worked fine. This was centralized to emotions that were augmented by frowning. So that was great. So all sorts of evidence like that coming in. And then finally, best of all, brain imaging studies. So you throw somebody in a scanner with or without Botox into these muscles there where they can or can't frown, and you show them stimuli of angry faces, upset faces, the sort of things that would evoke you frowning. And what you see is normal controls. As you sit there and you watch somebody with an angry face, it activates your amygdala. Amygdala, fear, anxiety, all of that. When you frown along with them, it activates the amygdala even more. Get people with Botox who no longer can frown, and you don't see as much of an activation of the amygdala. You don't see as much of an activation of a different part of the brain, the cortex, having something to do with empathy. Empathy, it turns out, when you were hearing some dreadfully awful thing done to someone, part of the empathy you're feeling for them is frowning at the terrible thing being done to them. That turns out that that lowers people's ratings of empathy, and it blunts some of the brain imaging responses to that. Okay, so that is incredibly cool and is telling us part of what we're doing is deciding how intensely we're feeling our emotions by our brain saying, well, how intensely am I smiling or frowning or generating some other expression? All of that said, these are not big effects. What you see is across a whole bunch of studies by now is it's not a strong effect. It is not all that reliable, but there's a subset of people whose brains are clearly deciding how strongly they are feeling emotions based on what their facial expressions are. as the final point of that, is the Botox going to do that to you permanently? In these studies, it was a small amount of Botox, which wore off after a while. So they were able to do before, during, and after, and show that after you went back to normal function, someone who's having, I don't know, Botox every couple of months and they haven't frowned since Jimmy Carter was president or something, whether that's going to cause a permanent change in this facial feedback information, that isn't clear at all.
To wrap up is a question from Ben from New York who says, I read you did research showing that chess grandmasters burn 6,000 calories a day during a tournament. Is that actually true?
It is not true that I did that research, and it is not true that chess grandmasters go through 6,000 calories a day. A shaggy dog tail. Okay, so history of stress physiology, the first 50 years or so, this guy named Hans Selye teaching everybody the body responds to a physical challenge, like somebody is trying to predate you by increasing your heart rate and your breathing rate, your sympathetic nervous system, your stress hormones, all of that. The stress response is something you activate in response to a physical menace, a physical challenge. And by the 1960s or so, a guy named John Mason at Yale was beginning to show, whoa, you could turn on just as much of a stress response in organisms with purely psychological circumstances. Circumstances where an organism, a human, feels like they have lost control, they have lost predictive information, they have lost outlets, showing you could get just as much activation of this physiological stress response. And there was this gigantic war between Selye, Hans Selye, and his followers, the physiologists, and John Mason and crew, the psychologists, as to whether stress was a topic for physiology or psychology. And they eventually got some sort of resolution in figuring out that psychological factors can turn on the stress response just as powerfully as can physical ones. Whoa, that could be great, because sometimes you could turn on a stress response for psychological reasons in anticipation of something that is really menacing and maybe happening. And sometimes you turn it on for no reason whatsoever, in which case we say you're being neurotic and anxious. The pitfalls of being able to turn on the stress response for anticipatory reasons when it turns out you're neurotically anticipating something that isn't actually there. Okay, so that said, in the aftermath of Mason sort of establishing this, people got very interested in, well, just how much can you activate the stress response with purely psychological states, with thought, with memories, with emotions separate of Selye. This is the part of the body that you activate when you're running from a lion. How much can thought cause your body to activate? And the way to think about that is, how much can thought activate your body so that it will deliver more energy to your brain, which is part of what happens during the stress response. And by 1970, a first study looked at this, of what's going on physiologically in tournament level chess players. These were very good players, ranked and all of that during tournaments. And this was a team at Temple University, Leedy and Leroy Dubeck. Dubeck, who was not only a physicist, but was also a chess grandmaster. And Leedy was a physiologist, and they got together and got a bunch of master's level chess players during tournaments to agree to be wired up to monitor heart rate, blood pressure, breathing rate. And what they came away with was, during these tournaments, extremely elevated heart rate, blood pressure, both systolic and diastolic, increased breathing rate, ranges of like 60 to 80% increases in heart rate. These are substantial increases. They had some subtleties in there. They showed it didn't make a difference if you won or lost. If you got a tie, you had the biggest physiological stress response. What they also showed was these were people in round robin tournaments. So over the course of repeated tournaments, these physiological indicators of a stress response got more and more pronounced. Okay, so that was great. That was published in a totally obscure chess journal and mostly ignored. And some decades later, a couple of studies starting to pick up on that. 2003, a study looking at chess masters during a round robin tournament, and they were looking at more details about the cardiovascular response. And what they did was replicate this initial finding. You have activation of the sympathetic nervous system. Autonomic nervous system, stuff you don't normally have conscious control over, comes in two flavors, two halves. Sympathetic nervous system, arousal, emergency, mobilization, parasympathetic, calm, vegetative. And what those studies showed was with each round of the round robin, more activation of the sympathetic nervous system in these players, more inhibition of the parasympathetic. And a very interesting sort of measure they did of parasympathetic tone, this obscure, fascinating, bizarre thing. It turns out your heartbeats, the time interval between your heartbeats varies a little bit from one beat to the next, interbeat intervals. And it turns out the more variability there is in that, that's a marker of a healthy cardiovascular system. And that's generated by the parasympathetic nervous system. And what they see is tournament chess players over the course of a tournament, over the hours, they have less and less parasympathetic tone. They have less and less heart rate interbeat variability. So that is another measure showing that. Then a few years later, another study looking at what are the implications of this sympathetic arousal, heart rate up, breathing rate up, blood pressure up, and you see a metabolic marker of it is you see a transition in the body that is seen, for example, in marathon runners. You see this in a subset of these tournament chess players, which is they burn through their carbohydrates in the first hour or so of the chess tournament, and then they switch over to fat burning. And that's a characteristic of marathon runners. So qualitatively, the same thing there. Then another study, 2004, showing elevation of glucocorticoid stress hormones, cortisol, hydrocortisone, the human version, and all of them basically showing the longer the tournament went on, the more activation of whatever version of the stress response they were measuring. Okay, so that's totally amazing. Then looking at this, I got this wonderful education. Last week, if you watched it, I had a chance to learn all about Jurgij Doja, who was a 16th century Transylvanian rebel who was this week, as a result of this question, I got to learn about esports. That there are people who are athletes who play like online games, like what is it? Call of Duty, other ones like in tournaments where they hand out gazillions of dollars to winners. And there are these athletes who play in these tournaments and they're televised and they've got commentators. And I discovered in the process there are more than 150 universities and colleges now in the United States that give out scholarships to people who are really, really good at these esports, where you sit there at your console for hours and hours and hours playing. And there's now a literature showing the same exact thing with esports. These people during these tournaments, blood pressure, heart rate, stress hormones, a metabolic transition, they're doing it as well. What has not been studied yet is what has to be the most interesting, bizarre sport out there, which is chess boxing, which is people who will play a round of high-speed chess, and then the bell rings, and they go box for 3 minutes of a round, and then the bell rings, and they go back to playing chess back and forth, and the winner either gets a checkmate on the other player or knocks him out. And this apparently is like popular in Russia. There's all sorts of chess boxing champions there. I assume that the dangers of that are that in the middle of the boxing round, both of them stop to figure out their strategy, or in the middle of the chess round, there's blood getting on the pieces. But this is a whole new area to look at in terms of intermittent physical arousal and mental arousal back and forth. Totally bizarre that that's out there. Okay, so that's what that story is. And what that's telling us is this is a very exciting domain where mere thought, intense thought in highly trained, focused people can activate some of the physiology of the stress response. Which brings us back to chess grandmasters ostensibly going through 6,000 calories a day during a tournament. So around 1990, somebody was interviewing me about psychological factors that can activate the stress response. And can you do this just with thought? And I said, yeah, this is amazing. There was even a study 20 years ago, chess players, while they're in the middle of a tournament, they're activating their sympathetic nervous system and their heart rate. And it's like it's a substantial rise. The person said, whoa, like how big of a rise? And I said, I don't know. It's like they're going through, I don't know, 6,000 calories a day they're consuming. And then I said, but please don't quote that. And the person did. Chess grandmasters go through 6,000 calories a day during a tournament. And I've been haunted by this ever since. There's no evidence for that. By now, about once every 3 months, I hear from somebody who's got a petition with the local school district about how they want to have chess being accepted as a type of phys ed, because it's well known that chess grandmasters go through 6,000 calories a day when playing a tournament. So I've been having to swat this one down because I winged it with that. And I've been teased at home about this ever since. And you guys know very well, every time I'm saying something like, oh my God, that's so expensive, or that's so something. And you'll say, what, like 6,000 calories worth? So I've been being tortured with this for decades.
And that is it for episode 64. Keep submitting questions at the form found in the Instagram story highlight and bio or the YouTube video description. I'm Offspring Sapolsky, and thanks for your continued support of science and the beard.